Alright, so let's continue on. You're going to use this equation a couple times, so I just don't want you to feel like where did this crazy thing come from? So I'm going to derive it. You don't need to memorize the derivation. You should be able to do it by yourself after seeing this, because we're using concepts we've already used before. And the main concept is net force equation, but we also have torque, because as you can see, friction by acting at the edge of this ball or wheel or whatever is a radius away, a distance away from the pivot point, which is, well, it rolls about the center of mass here. So this friction force is going to exert a torque on this ball here. So, but first we want to start off with a net force equation. So F net, because we're looking for the linear acceleration down the ramp. So the linear acceleration is going to come right here. This is the linear acceleration down the ramp, A net. And that's going to equal Fg sine theta pulling down the ramp minus F friction, static friction, going up the ramp. It's static because it's actually not sliding here, it's rolling. And rolling means that, as you saw in the previous slide, the velocity is 0 down here, and so that means in order for the velocity to be 0, it has to not be sliding, so that's static friction. Okay, but to move on, we gotta realize that this force of friction exerts a torque. So let's do a little torque calculation here, also using Newton's second law. Torque is I alpha. This is Newton's second law for rotation. It's like F equals ma. And the torque is given by the force of static friction, a distance of r. They have big R here. I'm just going to use little r. Well, no, I'll use big R. I think I can remember. And that's going to equal I alpha. But alpha, remember, is acceleration, linear acceleration, divided by the radius. So what we can do is, and the radius is capital again, I knew I was going to forget. So what we can do is divide the r over, so that the force of static friction is I a over r squared. I just took this r and brought it over here. So now we can take this expression for friction and stick it in here, so that this becomes now I called this A, so I'm just going to leave this as A just because it's A here. So realize it's still the net force. I'm sorry, the net acceleration down the ramp, but I'm just going to leave it as A. So MA is FG. Actually, let's turn this into MG right now. Mg sine theta minus I a over r squared. We want to solve for a, so let's get our two a terms together. So we'll add this term to this side, so we get ma plus I a over r squared equals mg sine theta. You can already start to see that it's starting to turn into what we want. We can then well, let's make r as a common denominator, r squared. So if we do this, then we also have to do this, right? Because when we separate it, this r squared and this r squared doesn't look like a 2. Would cancel out and bring us back to the normal MA, right? So we can do that. Then we could multiply both sides by r squared. So I'm just going to do this. Multiply this side by r squared. multiply this side by r squared, which is going to cancel this r squared. So let's just delete that. And then we'll take out a common a. So a m r squared plus I equals mg sine theta r squared. And then we can divide both sides by this. I'm not going to write it twice. You can imagine that. Plus I. So that goes bye-bye. A equals mg sine theta r squared over mr squared plus I. And we're basically here, we can just do a slight bit of rearranging. We're going to do another common denominator. Basically, we're going to divide, well, no, we're going to multiply by mr squared. Let me just undo that. So if we pull out of mr squared, I'm just going to rewrite it. Mg sine theta r squared. If we pull out of mr squared, then this first term is mr squared, so that's just going to be a 1, right? Basically, you can check me by redistributing. So this times this should equal that. This times this, right? If you multiply this times this, the mr squares would cancel and leave you with I. So that's basically undistributing. And then this mr squared cancels with this m and this r squared, and we get our expression g sine theta over 1 plus I over mr squared. So that's where that comes from. Not too shabby, huh? And you can see that if something is not rolling, then there is going to be no ICOM, because if it's not rolling, then there's no radius of, from the pivot. This is not defined for something that's not rotating. So this becomes 0, and then this becomes a equals g sine theta, and we have something just moving down a ramp translationally, or in other words, sliding down a ramp. And you should be able to see really quickly that a yo-yo is really the exact same situation. We got gravity pulling down the ramp. Now remember, in this case, the ramp is 90 degrees, so the ramp is vertical. It's so steep that it's just straight up and down. So we still have gravity pulling down, parallel down the ramp, but in this case, it's just gravity straight down. And then we have something exerting a torque. It's not friction this time, but what it is, it's the string. It's a tension in the string, and it acts this little, depending on where the string is. What makes this a little more complicated is that the radius changes as the string winds up. But anyway, there's still a radius, and so that, because the force is exerted on a radius, or a certain distance away from the pivot point at the center, it's going to exert a torque, and that's going to cause it to spin. So sine of 90 is 1, so this sine term disappears, and we just get this for yo-yo. Cool. Let me try to finish this up in this video. I don't know if it's going to happen. The next topic is angular momentum. Again, it's the rotational equivalent of linear momentum, but we have a little extra piece, and it's a cross product. But first off, just like regular momentum, P was mass times velocity, angular momentum, script L, is rotational mass, I, times rotational velocity, omega. But we can also exert angular momentum as a cross product, and strangely enough, the angular momentum points perpendicular to both the radius and the linear momentum, or in other words, the velocity. In this cross product, we can take P, which is mv, and split it up so that we pull m outside, because m is just a constant, and it's the velocity really that's acting perpendicular to the radius to give angular momentum. So we do the cross product of r cross v, and you'll need to use the right-hand rule for this, which we did way back in chapter 2 or 3. I already forget. And don't forget the convention that positive k is towards you. So x, positive x is to the right, negative x to the left, positive y up, negative y down, positive z out towards you, like this is pointing towards you, and negative z away from you. You can also, just like you did conservation of momentum with this, and you have inelastic collisions, elastic collisions, you can also do conservation of angular momentum, and you have a problem where you have an inelastic collision with a record player and some putty, and so you'll need that for that problem, conservation of angular momentum. I could play a video. There's a really cool demo. Maybe I'll play a video just at the end, and you know, it won't make the video longer than 15 minutes maybe. Well, anyway, let me just talk this last topic, and then I'll play the last video, and hopefully it won't be longer than 15 minutes. So let's revisit torque. I mentioned torque in chapter 10, but just as an extension of angular momentum, the relationship between force and linear momentum was that force was the derivative of momentum with respect to time, and this led to like impulse and all that good stuff. We're not going to talk about rotational impulse, but you could. But the rotational equivalent of this is torque is the derivative of angular momentum with respect to time. So you just, if you have a angular momentum function, take the derivative, and that will give you the torque. And just like work is force times distance for a constant force anyway, work is torque times the rotational displacement. Yeah, so you'll use those in one problem anyway. This in one problem, this in a couple of problems, but it's pretty straightforward. Now let me find the video that demonstrates how angular momentum is perpendicular to both the velocity and the radius. It's pretty cool. Alright, I don't know if you'll be able to hear this. I forget if I had the settings so that you can hear the internal sound. Speaking through a mic right now, but anyway, I'll play it. If you can hear it, that's cool. If not, I'll do some explaining after, just to sum up.
Suppose I have here a string, a rope, like we have there. And I stick into that rope, I attach to the rope this wheel, just like so. And I let it go. Well, we all know it will happen. Clunk. It's clear. All right. But now I'm going to spin it before I let it go. Where's the wheel? The wheel is here. So we'll spin it up, and then we'll put it in here. Notice the way I'm spinning it. I'm holding it away from you now. I'm going to change it and do it differently next. There it goes. About 10 seconds. Isn't that amazing? And it rotates seen from below clockwise. Now it's going this way, and I'm going to redo the experiment, changing the direction of rotation, and then it will go the other way around. And now the angular momentum, is it rotating like this, is pointing here. Spin angular momentum is pointing like this. Torque is like this. And so the spin angular momentum is chasing that torque. I'm the spin angular momentum, I'm the torque. This is the torque. It's chasing it. All right, so I had this in my right hand. That's all right. And now I will, so when I spin it up,
Alright, I'll just stop it there. So I put my microphone up near the speaker. I hope that doesn't sound screwy. Um, but yeah, so anyway, I just wanted to talk about how, if you remember in the video, or at least you saw him pointing. I don't know if you definitely heard it because I put the mic up. Anyway, um, the velocity. So you have the bicycle tire. I'm gonna try to draw it like as an angle here, and you have like the spoke, not the spoke, the like the handle. So you know how he was holding it, like basically his hands are grabbing onto some handles at the center here, right? So I'm drawing those handles right now. Of course, you got the spokes going down. So I don't know if you can really see what I'm doing here, but if I were to draw an XY axis, the y-axis, the bike would be, the tire would be in the y-axis. The x-axis, the z-axis, is going to be essentially the tire. So here's the y-axis and the z-axis. The tire is in the y-z axis. Can you picture that? And then the handles are in the x-axis. I don't know if the way I drew it is very good, but I tried to draw the tire tilted, not like straight on, so not like we're looking at the face of the tire, so that the handles would become pointing towards us. I wanted it tilted. Anyway, long story short, the angular momentum points along the x-axis because, according to the right-hand rule, you got the radius, which is like the spokes, and you have velocity, which is tangent, depending on which way it's rotating, tangent to the tire. So if you do the right-hand rule, you basically take your fingers and you move them up along the radius, curl them in the direction of the velocity, and your thumb points that way, this way. And if this is so, you should ask me to demonstrate this for you. It's really hard to do without me having a hand on here. But anyway, then you get conservation of momentum, and so that's what sort of makes it magically. It's not magic, but it appears to be magically hovering in the air. But in order to conserve momentum, it has to stay up like that. So anyway, that's pretty cool. All right, that's it for chapter 11, and I'll do some sample problems from the book. See ya.